Thank you all for joining me, and right now I'm just going to update some earthquake activity. Okay, so we've been having some pretty strong earthquakes here in Iceland at a 5.4. Most of the quakes, if not all of them, they're not concentrated here, but right here. That is where most of the quakes are concentrated, but there's a chance that the magma dike might be moving southwest. That's kind of concerning, guys, because since this magma dike is moving towards the southwest, this could mean that there could be some intrusion towards the southwest. It could be the crack could be opening up on the ground towards the southwest, and that is very concerning. Hold on, I'm just looking for something. I'll be back in a second. All right. I found what I was looking for. Hold on, I'm gonna unplug this. Unplug this. Hopefully you can hear me again. Yes. Okay, perfect. You guys can hear me better now. All right. That's why I didn't really use this much. All right. Much better. Much better. All right. So 5.4. Let's look at Campi Flegrei. Just make sure I got the right website. I'm going to try to load the site. All right. It is Portal. Okay. P-O-R-T. That's the one I was looking for. That's the seismogram website. Well, web recorder. So this is from Campi Flegrei. There was actually a pretty strong earthquake earlier today, up to about 1.5 earlier today. So nothing really going on right now. But it was earlier today, so that there you can see right here that little green line there. Yeah, and you can see it here too, right around 17. Yeah, that's a quake, and you had another one right around 1735. Seismolab. There's the 1.5 right there. Oh, sorry. There's the 1.5. That took place at 15:59 local time, which is 16Z time. And then right around 16, you had right around 1630. That's 1630, and that was 1735. So you're right around 1735. So you had a small quake around 1730. And then around another one in 1735, and yet they did not count that one for some reason. See, 1729, 1730. So they counted this one, they counted this one, but they didn't for some reason count those two quakes. Let me look around. Maybe those were from Vesuvius. Let me see. Nope. Those were definitely Campi Flegrei quakes, but they didn't count them. That's Ischia, Campi Flegrei. So yeah, they didn't count those quakes. This actually was larger. So this was a 0.7. I would say that the quake that happened after was maybe about a 1.0 at least. Not a 1.5, maybe at least a 1. And tomorrow is the day we're going to get info on the uplift, I believe. Or 2 days, actually. Considering today's the 14th. Mm-hmm. Let's see. OV dot. Okay. OV dot. Okay, that's the one I was looking for. March 9th. So the 16th. So in 2 days is when we're going to find out the state of the uplift. So there's some quakes. Ooh, pretty darn shallow. This most powerful quakes. Red is more powerful and more recent. Pretty close to the surface, so there's a lot of magma intrusion going on. Could also be because of rock fracturing too. Okay, so let's look at the uplift right now. Alright, so uplift has been continuing pretty steadily for the past few years. In fact, okay, let's go down to 200%. Alright. So here's when the uplift, in the last 10 years, we have about 70 centimeters of uplift, basically, or about 720. Because from 0 right to about what we are now at. Yeah, we just have surpassed the 720 centimeter mark. Yeah, it's 720 centimeters. Okay. So when are we going to surpass? Oh, okay. So here's. So the at the rate we're going here, we're going to surpass 40 centimeters, probably somewhere between 2021 and 2015. So like January, February, March, April, May, June. So yeah. Right now we're in March, so this is where we are right now. Right about here. So that means, the rate of uplift is pretty, it increased here, and then it stabilized, and then it just started steadily increasing. Like, it's not increasing in speed. That's the good thing. It is a steady increase of uplift. The uplift right now is pretty steady. It's nothing like what happened in 1972 and 1985. It's not, or 84. The uplift is fairly steady. That probably would have been a little scary, but it is this uplift that is causing the earthquakes. And why is it constantly uplifting? Is because you're having a lot of pressure building up. Basically, you're having all those trapped gases building and building and building and building and building. And this building of the gases and also influx of magma causes the ground to rise up. The thing is, the Pozzolana caprock is like cement. It's basically Roman concrete. But you know what happens to the Roman Colosseum during an earthquake? It cracks. It is very strong, but it's also not flexible. So it's not going to be able to withstand all this uplift and subsidence. Uplift and subsidence. Eventually, that will cause the caprock to break, magma to basically go through the caprock and erupt on the surface. They found the presence of magma very close to the surface. In fact, I'm going to type in Campi Flegrei. No, not magma chamber, just magma. I'm going to go to news. No. Yeah. Okay. Oh my God. All right. They're probably going to talk about roaring, that the people could be hearing a roar, like a roaring sound. There has been no damage. Okay, of course, a 1.5 earthquake. And more of a now continues. English. $20 resin rate. Yeah, that is insane. Since January 2011, that is to say, in the last 10 years, the soil in the Campi Flegrei has risen by 70.5 centimeters. The fault of Bradicism. The phenomena of raising and lowering of the soil, typical of the volcanic and seismic area, which includes Pozzoli, Baccoli, Quartro, Monte di Procida, and the Phlegrean area, and extends to the western outskirts of Naples. This can be seen from the weekly monitoring bulletin of the Campi Flegrei of the INGV, National Institute of Geophysics and Volcanology. Yeah, 57 earthquakes, 1 to 1.5. Okay, yeah, that's not what I want to see. I want to go back like a couple months at least. Okay, I'm back now. Smoke Tau volcano? Oh my god. Thanks for letting me know, dude. 74 quakes. $10 meters high. Okay, that's nothing bad. 596 tons per day. Okay, yep, magma's intruding back in the volcano. Okay, Twitter. And 49 episodes of volcanic tremor of 1 to 2.5 minutes. A short-lived 4 to 500 meter tall white plume was generated by a burst of steam-laden rich gas from the main crater and lasted 2.5 minutes. Increase unrest. Okay, level 2. $74. 46 tremors. 1 to 4 minutes. Fumarolic events. 596 tons per day. Temperature highs of 71.8 degrees Celsius and pH of 1.59. Very slow and steady inflation and expansion of the Tal region since the January 2020 eruption. These parameters may indicate increased magmatic activity at shallow depths below the edifice. Well, beneath the edifice, well, whatever. 71, and let's see what the temperature was here. 71.8, 582 tons on the 13th. And 2 days later, let's see what happens. 71.8, still 71.8, and it was about 500 tons, and let's see. 596 tons. That is pretty high. Temperature highs of 71.8. Let's go on the 13th, right? And I'm trying to go to the 12th. Alright. Pinatubo? Wait. What? Pinatubo? That is the level 1 abnormal. Wow. Okay, that is scary, guys. Pinatubo's acting up. I'm gonna send this to my friend. Okay, let's go back to the Rick. Okay, so we had a 5.4. We had some 4s, a couple 5s. Okay. So let's look at the weather for the next few days. From what I can tell, I don't think there's going to be any severe weather though in the Northeast for at least, I think, until at least late April, early May, because we're going to be in a really cold pattern. Okay, this is all going to be rain events. See, rain. Yeah, this is going to be a storm system that's going to miss us to the south. Another rain event. Possibly snow. Possibly. Just so this is going to be a light snow event. Quick duration. This storm's going to go miss us to our south. And then what's going to happen is this. Okay. All right. Twelve was pretty insane though. Not with the cold or snow, but I mean not with the snow, but with the cold. Boom! Look at that. It is insane. Whoa. Oh, wow. Okay. Thermal precip accumulation. You know which model I really want out of all of them? I want number 5, 16, 18, and 20. Yep. I want 5, 16, 18, 20, and 2. So I want 2, 5, 11. Oh yeah, 14. Okay, so here's the ones I want. I had a choice. I would take 2, 5, 2, 5, 6, 11. Let's see, is 11. Yeah, 11. 13. 14. 16. 18 and 20. And let's see. Oh, look at that. 13 and 20. Let's see. Three. Well, let's look at the tall earthquakes. Okay, let's look at the more recent earthquakes. Batangas, no. Any shallow quakes in Batangas? Any shallow quakes? No. Okay. There it is. March 14th. Okay. 46 tremors, 71.9, 1.59, 596 tons a day. Oh, wait. So, let's see. Let's look at the Storm Prediction Center. Yeah, well, that was the last time I was looking at it was in 2020. Wind, hail, tornado. Isn't that weird? They're talking about a snowstorm, and yet at the same time, there's also talking about severe weather. Yeah, that's pretty insane. It looks like Goodland, Kansas might get some severe weather. And Denver, yeah, is getting snow right now. Oil prices should be right about $65. Let's look at the USGS. I'll show you guys if there's any earthquakes here in the United States. I'm only going to do this till 9 p.m. because then I have to go. Oh, you had a 3.9 just now in Kansas. Yikes. This is all because of fracking, of course. These are fracking related quakes. In fact, if you're going to go earlier, you said 438 people felt that one. Probably 500. Oh my gosh, 1,700 people felt that one. Well, this one just occurred just in the last hour. 1,480 people reported feeling that quake. There's even some slight felts as far south as northern Oklahoma. There's even some felt reports down to the Oklahoma border near Arkansas City. There's been a felt report. It's a very light shaking. Wichita reported some light shaking. Damage, none. So there should not be any damage. Maybe very light near Wichita. Oh wow, this quake occurred right in the Wichita area. Yep. Wichita News. Yep, 3 small quakes. Yep. Wake up call. Wichita, let's see, latest. Okay, no, that's not what I want. Wichita earthquake. Our report felt it loud boom associated with it, west side of Wichita. It reported an epicenter in East Wichita. Charles Koch. Yeah, the Koch brothers. More earthquakes today.
Please enter your access code followed by the... Your entry is not accepted. Please... Welcome to the Automated Customer Service Center of New York Community Bank. Checking information, press 1. For safe, for your current balance,
I don't have a lot of money, unfortunately. I think you guys can hear me, though. That's the problem. I muted my mic, but I think you guys can still hear me. That's what I believe. Let me see. Yeah, I think you guys can still hear me. Okay, because I'm muted, but I think you guys can definitely still hear me. So let me see. Yeah, it looks like it's still working. A new 5 Oaks update. A new update. Nothing yet. I'm still waiting for the new update. For the one for today, the 14th. Or the 15th, actually. It's already the 15th in Towel, so I'm still waiting for the new update. Okay. Okay. So let's look at the... Alright, I'm going to go back to the website to... Okay. So some 3s. A couple of 3s. Nothing much to complain about, though. Reykjanes Peninsula. Reykjanes. Reykjavik. So I'm going to be ending the stream soon. Okay, so nothing much is going on right now. Yep. October 1971 was when the email was sent. Yeah, that's definitely what it's like. Yeah. Of course they commit atrocities. Of course. Whatever. Helicopter fuel, yeah. Referring to Pinochet. Do you know what Pinochet did? And guess who installed Pinochet into government? Richard Nixon. But we're not going to talk about that right now. We're focusing on earthquakes and volcanism. Yeah, this is a swarm that is likely induced by fracking. This is definitely a fracking-induced quake. They're all really shallow, right at 5 kilometers. That's probably where the shale rock is. And that's probably because of, when you inject groundwater into there, it lubricates the fault, and so the faults start moving because of water. So, Mount Peck 2 is actually not a hotspot volcano. I actually had a feeling that the subduction zone was actually because of the subduction zone. The Pacific plate goes under, is going under the Eurasian plate, and what's happening is you're having a lot of water being carried down, and so because the plate becomes stagnant, and the stagnation, but also it releases water, because it quakes, and so this causes magma to rise to the surface. It actually is subduction. Well, the MTZ. No, what's happening is it actually is subduction. So you see that area of dark blue? That's actually water from the Pacific plate. That's actually the Pacific plate being under. I'm going to show you. See? Aha! Pacific plate. So this is actually subduction driven. So the mantle transition zone right here. Okay. So brings water. The water causes the melting point of the rock to lower, forms magma, rises to the surface, and you have a volcanism. This is exactly what I think.
What is the cost per credit of a WGU degree?
Well, not the process, but I was generally right. I thought it was something like that. Once I knew that magma, water loads and melting point of rock and generates magma, I thought that was kind of what was going on.
Unlike most universities, we don't charge tuition per credit hour.
And it's basically that. So let's watch this video. Of course, what's this channel?
This is Mount Peck 2, also known as Chengbai Mountain by the Chinese. It lays here, in Northeast Asia, on the border between China and North Korea. Although few outside the region even know it exists, the enormous stratovolcano is one of the largest and most dangerous volcanoes on Earth. Its massive caldera, which today is partially filled by an equally massive crater lake, has an area of almost 20 square kilometers. That's more than 5 times larger than the caldera of Mount St. Helens. The eruption that shaped the caldera around 1,000 years ago is considered to be the second largest volcanic eruption in the last 5,000 years. Classified as a 7 or supercolossal eruption on the Volcanic Explosivity Index, it ejected more than 100 cubic kilometers of material, enough material to bury even villages more than 1,200 kilometers away in northern Japan under a thick layer of ash. And yet, despite its size and its destructive past, Mount Pektu was for the longest time, and to some degree still is today, a mystery. Even for the scientists that have studied it, the volcano And yet, despite its size and its destructive past, Mount Pektu was for the longest time, and to some degree still is today, a mystery. Even for the scientists that have studied it, the volcano remained a conundrum only until very recently. Nobody could explain why exactly here, in a tectonic sense, in the middle of nowhere, one of the largest volcanoes on Earth exists.
I've always loved sci-fi, and the idea of being right on the edge of it.
To understand why Mount Pektu is so unique, we first have to understand what makes ordinary volcanoes, well, ordinary. Take a look at this map. It is a map of all the active volcanoes in the Pacific. Most of them run along clearly visible lines, almost like a string of pearls. Why this is becomes clear when you lay a map of the tectonic plates over it. Almost all volcanoes are found along plate boundaries, more specifically along subduction zones, so zones where two plates collide and the denser oceanic plates are pushed under the continental plates. Here in Japan, for instance, where the Pacific plate is being subducted beneath the Okhotsk and the Philippine Sea Plate, and where the Philippine Sea Plate is in turn being subducted beneath the Eurasian Plate. As a consequence of these complex subduction zones, Japan is one of the most volcanically active regions in the world. In total, the small island nation has over 100 active volcanoes. The fuel of this subduction zone volcanism is, slightly ironically, water. Oceanic crust holds huge amounts of water, stored in hydrous minerals which form when crust interacts with seawater. As the subducting slab descends into the mantle, it encounters greater and greater temperatures and pressures. This ultimately, at depths of around 120 kilometers or 75 miles, causes the rock to change its chemical composition and release the water that was trapped in the crust into the mantle above. Water added to the hot solid mantle lowers its melting point because the water molecules weaken the crystalline structure of the rock, much in the same way that salt weakens the crystalline structure of ice. The magma produced this way then rises up into the overriding plate, collects in magma chambers, and eventually causes volcanic eruptions on the surface. And so, a volcanic arc that runs parallel to the subduction zones is created along the plate boundaries. A similar pattern can be found all around the Pacific Ocean, like here in Indonesia, or in Chile. In fact, almost 80% of all active volcanoes on Earth run along the numerous subduction zones in the Pacific, which is why the region is commonly referred to as the Ring of Fire. We already know this since the 1960s when the model of continental drift, first proposed by Alfred Wegener in 1912, was finally proven, and together with the model of seafloor spreading combined into the theory of plate tectonics. There was only one problem. There were still a few volcanoes that didn't conform to this theory. Volcanoes that were seemingly sprinkled across the globe at random. Like here, in Hawaii, some 3,800 kilometers or 2,400 miles away from the next plate boundary, or in Yellowstone. Chiang Mai Mountain, which sits more than 1,000 kilometers northwest of the Japan Trench, is another one of these weird interpolate volcanoes. To explain this kind of volcanism, a new model was needed. An important clue to solve this mystery could be found on the ocean floor in the North Pacific. If you follow the line of islands that make up the Hawaiian archipelago northwest, you can find a series of volcanic structures that once formed very similar islands before millions of years of erosion reduced them to a series of atolls and seamounts. This so-called Hawaiian Emperor chain contains more than 80 individual structures like this, stretching nearly 6,000 kilometers or 3,900 miles across the ocean floor. On first glance, you might come to the conclusion that the source of Hawaii's volcanism must be moving from northwest to southeast, like a giant marker drawing a line across the Pacific plate. However, you can also explain this line in a different way. The same pattern would be produced if instead the oceanic floor is moving. To this realization came the Canadian geologist John Wilson, too, in the 60s. The movement of the Pacific plate from southeast to northwest above a stationary source of magma would also produce this image. And sure enough, this is exactly the current path of the plate. Such volcanism that isn't influenced by plate tectonics would need to have a much deeper origin than other volcanoes. This idea was then developed into the mantle plume model. It explained these volcanoes as hotspots that are fed by enormous upwellings of hot mantle rock that rise to the surface from the depths of Earth's mantle, driven by heat exchange across the core mantle boundary, 2,900 kilometers or 1,800 miles below the surface. And while it would take a few more decades before technology had advanced to the point that it could actually prove what Wilson had only hypothesized based on a few pieces of evidence, there was finally an explanation for intraplate volcanism. With this, the puzzle surrounding the source of the mysterious volcanoes in places such as Hawaii, Yellowstone, and Northeast Asia seemed to be solved. There was only one slight issue. Mount Pektu is not such a hotspot. Scientists wouldn't realize this until the end of the 20th century.
I've always loved sci-fi, and the idea of being right on the edge of discovery and the frontiers of space. And doing exploration in Eve allows me to do all of that stuff. You get to use cloaking devices.
One reason the mountain has remained elusive for such a long time certainly has to do with its location. It not only lays in a very remote region of Asia, it also sits at the border of two countries that lived in almost complete isolation for much of the 20th century. It was only once China started to open up more and more to the outside world in the 80s and 90s and began to promote scientific research that gathering information about this solitary giant became less of a political impossibility. Still, it wasn't until the end of the 90s that the first permanent seismographs were installed on the Chinese side of the mountain. And this was hugely important because seismographs had become perhaps the most essential tool for studying the geology of Earth's interior. That's because of one clever invention: seismic tomography. In the 1970s, computed tomography, or CT scans, revolutionized medicine by giving doctors the ability to look into their patients' bodies without having to make any cuts, and that way look for tumors, fractures, infections, and a variety of other problems and diseases safely and effectively. Geologists realized that they could adopt this technology for themselves to finally reveal what's going on hundreds or even thousands of kilometers below our feet. Because the seismic waves produced by earthquakes move at different speeds depending on the temperature, density, water content, and state of the rocks they travel through, you can measure the arrival times of these waves at various points on the surface to map out the interior of our planet. This allowed scientists to quite literally cut open the Earth and see what's inside. Like medicine before, this technology revolutionized Earth science. Finally, it was possible to see processes that were long hypothesized, like the subduction of plates into the mantle, the formation of new ocean floor through upwellings of hot mantle material below mid-ocean ridges, and of course plumes that rise up from the core mantle boundary and feed hotspots, such as Hawaii and Yellowstone. And so, for a brief moment in time, we had an explanation for every form of volcanism on the planet. All three forms, subduction-induced volcanism, mid-ocean ridge volcanism, and mantle plumes, were supported by evidence and seemed to explain every volcano or volcanic structure on the planet. That was until the first tomographic models of Mount Changbai appeared in the late 90s and early 2000s. What they showed was significantly different from what images of Hawaii or Yellowstone showed.
I've always loved sci-fi, and the idea of being right on the edge of discovery and the frontiers of space. And doing exploration in Eve allows me to do all of that stuff. You get to use cloaking devices, probes to scan
There wasn't the prominent low-velocity anomaly extending all the way down to the core mantle boundary. Instead, the anomaly seemed to end roughly 400 kilometers or 250 miles below the surface, which is deep, much deeper than the source of any volcano near subduction zones, but not nearly as deep as the 2,900 kilometers or 1,800 miles geologists had expected. Not only that, but below the low-velocity anomaly, there was a distinct high-velocity anomaly that showed up in the images at depths of about 600 kilometers or 300 had expected. But not nearly as deep as the 2,900 kilometers or 1,800 miles geologists had expected. Not only that, but below the low-velocity anomaly, there was a distinct high-velocity anomaly that showed up in the images at depths of about 600 kilometers or 380 miles. Right here. It showed what appeared to be a large barrier of unusually cold material. This puzzled the geological community. Once again, there was a form of intraplate volcanism that couldn't be explained. That wasn't a typical hotspot like previously thought. One of the largest volcanoes on Earth suddenly didn't seem to fit into any existing category. It was a completely volcanism that couldn't be explained. That wasn't a typical hotspot like previously thought. One of the largest volcanoes on Earth suddenly didn't seem to fit into any existing category. It was a completely new kind of volcano. To understand what's going on here, we first have to understand this zone. Curiously, the cold anomaly observed here sits right inside the so-called mantle transition zone. This is the known transition zone between the lower and upper mantle. Here, the pressure is great enough that it changes the internal arrangement of the atoms by forcing the rock into a much denser, more compact crystalline structure. This results in a sudden, quite significant jump in viscosity in the zone. Because of this, the mantle transition zone acts as a sort of barrier in the mantle, which at least partially separates the processes in the upper and lower mantle from one another. Geologists quickly realized that the distinct anomaly of cold material in this zone can only be a piece of ancient crust. Expanding the image further to the east quickly revealed which plate it is. It appears that the Pacific plate, after subducting into the mantle, bends horizontally and becomes stagnant in the mantle transition zone right below Mount Pektu. This wasn't even that surprising. Ever since we began to understand more about the interior of our planet and its layers, it has been speculated that slabs after their subduction would become stagnant here. In fact, there was a fierce debate going on in the geological community, with one side arguing that the convection processes in the upper and lower mantle are separated from one another and that slabs after their subduction become stagnant in the boundary layer, while the other side argued for whole mantle convection and subducting slabs sinking all the way to the bottom of the mantle, forming a graveyard of slabs on top of Earth's core.
They're both correct.
But before you think clearly the first group had it right, here's an image of the subduction zone just a few hundred kilometers to the south. Here, you can clearly see the Pacific slab penetrating the mantle transition zone and sinking into the lower mantle. Likewise, global seismic tomography models have revealed an entire catalog of roughly 100 old slabs that have penetrated deep into the mantle. So clearly it's not as simple as picking one model over the other. That aside, there was also the question how a stagnant slab could even produce volcanism so far away from the subduction zone. Earthquakes provided an important clue. Most earthquakes on Earth occur, just like volcanoes, near plate boundaries, where the crust is bent and deformed by the collision of the plates. But seismographs in Asia also frequently pick up strong earthquakes deep below Mount Qingbai, 600 kilometers or 380 miles below the surface. Remember this chart, it'll be important later.
Hi, I'm Phil. It's hard to make a good impression on video, which is why we made It's like Instant Weekend Update, a simple way to be interesting on camera. Works with Zoom and WebEx and just about every other video system for meetings or streaming or just making recordings, and it helps you not feel like an anonymous head in a box when you're making videos. Here's how it works. First, you choose the room that you want to be in. We've got hundreds, from kind of realistic, simple ones to more cartoony ones to stuff that's fun but also obscures your real background if you don't want people to see the clutter in your house. I kind of like this one the best. I don't know, I just find it calming and relaxing. And then you use slides to wake up your presentations. Now, I originally wanted to use them so that I could show off my collection of Instagram photos of things in Japan with really awesome names.
really miss this place a lot. But you can also use just to present. Now, when you normally present over video, you have to go through this awkward dance of, I'm going to share my screen, can everyone see my slides? And even when it works, you're asking the audience to split their attention, to choose between looking at you and looking at your materials, which isn't ideal. With you can type in simple slides right in the app, and these will automatically change appearance when you change rooms, so that you can find exactly the right mood for whatever message you're trying to convey. And a lot of
Here, our story takes a bit of a turn because this chart, it'll be important later. Here, our story takes a bit of a turn because at the start of the 20th century, earthquakes became the center of discussion for a different reason. In 2002, the newly established Tianjin Volcano Observatory started to pick up a worrying increase in seismic activity 5 kilometers or 3 miles below the mountain. Over the next year, the number of earthquakes increased from an average of 10 per month to over 100, in some months even over 200, signaling that an outbreak might be imminent. If we look at Mount Qingbai's eruptive history, we can see that it can be broadly divided into 3 evolutionary stages. The volcanic activity started around 20 to 30 million years ago as part of the large-scale intraplate volcanism that took place in Northeast Asia since the late Jurassic period. Around 2.5 million years ago, partial melting in the mantle below the volcano increased significantly and resulted in the eruption of extensive amounts of basaltic lavas, which even today cover an area of around 10,000 square kilometers or 4,000 square miles, with an enormous shield-like plateau, the largest in the region. Due to the enormous weight of this plateau, the rise of the magma below was eventually slowed down, so much that it began to collect in a shallower magma chamber before erupting to the surface. This was actually very important, as the extra time changed the chemical composition of the melt due to contamination from the crust and the deposition or removal of certain minerals in the magma. As a result, the lava that erupted onto the surface became a lot more viscous, which led to the formation of a volcanic cone on top of the basalt plateau. This second phase lasted from around 1 million to 4,000 years ago, and by the end of it, had produced a cone roughly 4 kilometers or 13,000 feet high. The last stage, the explosive stage, then resulted in the almost complete destruction of this cone, which brings us back to the millennium's eruption of 946. This enormous eruption blew off the entire top half of the volcano, creating the caldera that we see today. If you imagine the amount of material that must have existed between the 2-kilometer high surface of Heaven Lake that partially fills the caldera today and the once 4-kilometer high summit of the volcanic cone, it's not difficult to see that the millennium eruption must have been one of the most catastrophic eruptions in human history. It produced a plume of smoke and ash that shot an estimated 25 kilometers or 15 miles into the stratosphere and ultimately covered more than 350,000 square kilometers between northern Korea and the Kuril Trench in 5 to 10 centimeters or 2 to 4 inches of ash. That's an area larger than the entire Korean peninsula. The total amount of ash dispersed by the eruption would have been enough to bury the whole of New York City under almost 150 meters or 500 feet of ash. Additionally, pyroclastic flows, avalanches of superheated gas and debris, filled valleys and canyons as far as 50 kilometers or 30 miles in every direction, burning an area the size of Tokyo in the process. At the time, the area around the mountain and Northeast Asia in general were not particularly densely populated, but today more than 1.5 million people live within the immediate danger zone of the volcano, and almost 1 billion people live within the potential fallout zone. Within this 1,500-kilometer radius, you can find many of the largest cities in the world, such as Seoul, Pyongyang, Tokyo, Osaka, Beijing, and Shanghai. If only 1 or 2 of these megacities would be buried in volcanic ash from a similarly strong eruption, the damages caused by that could easily make it one of the most costly natural disasters in history. But in mid-2005, the mountain went silent again. The seismic activity went back to its pre-2002 levels and has remained that low ever since, making an eruption within the next few years unlikely, at least at the present day. But what these years have shown us is that the volcano is very much active and will likely erupt again at some point in the future. This ignited the scientific interest in the volcano and resulted in a flood of new research, primarily from China. Mount Pektu's sudden unrest even got the normally very reclusive North Korean government worried, to the point that they started to reach out to the West and eventually even invited a team of scientists to the country to study the volcano. Together with their North Korean colleagues, the group collected data, took rock samples, and installed a set of seismographs to monitor the mountain. The first results of this unique collaboration were published in 2016.
Did you know that the average adult has 5 to 20 pounds of toxic poop in their body at any given moment? Seems crazy, right? All that poop just sitting there, rotting away inside their intestines and colon. Is it any wonder that colon disease is on the rise with all this waste just sitting inside your body? Most of this waste contains chemicals that your body rejected, but due to certain issues like constipation, you couldn't flush it all out effectively. So if you're feeling sluggish, bloated around the waist, or even just plain backed up, then give Zupu a try for 14 days. It will clean you out, guaranteed. Click through to read the hilarious reviews about how consistently effective Zupu truly is. It contains the perfect dosages of all natural ingredients that will get things moving and flush out that extra waste you're carrying around. You'll feel amazing when it's gone. As this toxic waste builds up, your body becomes a walking vessel of fecal toxicity. Once this happens, you begin to experience excess fatigue, weight gain, digestive issues like IBS, leaky gut syndrome, constipation, and diarrhea, skin conditions like eczema, psoriasis, rosacea, and acne, brain fog, focus and attention issues, mood swings, anxiety, and depression, and that's just the beginning. It might be a bit embarrassing to talk about your poop, but it has a huge impact on your health, and it's something that you have to understand if you want to look and feel your best. It might come as a shock, but your digestive system impacts the health of your entire body, and understanding the health of your digestive system begins with understanding your poop. If you're not...
I am so sorry about that. You guys didn't need to see that.
With
I'm
all the
sorry.
new research that has been done over the last 10 to 20 years, we now have a pretty good understanding of what causes this unusual form of volcanism. Using the latest seismic tomography models, created taking nearly 80,000 earthquakes recorded by over 3,000 seismic stations, we can now map the mantle below Northeast Asia with never-seen-before clarity. From here, we can create a schematic 3D model of the main features that drive the volcanism under Changbai Mountain. Let's start with the most obvious one, the Pacific Plate. As you can see, a huge portion of the slab has become horizontal and stagnant under Northeast Asia after subducting at a roughly 30-degree angle below the island of Japan. In the process, it has trapped much of the upper mantle in the region between the crust and itself, creating what geologists have termed a big mantle wedge under the Korean Peninsula and East China. Also of note is this gap, roughly at 35 degrees northern latitude. Here, the Pacific Plate is visibly being torn apart at depths of around 300 kilometers or 190 miles, with the southern part descending at a much steeper 70-degree angle and subsequently penetrating the lower mantle. The length of the western edge of the stagnant slab, which is much longer than the corresponding part of the subduction zone, indicates that these two pieces were once joined together, before they were ripped apart, likely as a result of the huge forces generated by the differences in the subduction rate, direction, and angle. Focusing on the mantle below Mount Pektu reveals a prominent low-velocity anomaly of partially molten rock that sits on top of the stagnant slab and has a diameter of roughly 100 kilometers or 60 miles. It can be described as a plume that rises from the mantle transition zone. This is an important distinction because unlike normal mantle plumes that are relatively unaffected by the tectonic processes near the surface, this plume seems to be the direct result of these processes, namely the subduction and stagnation of the Pacific Plate. Furthermore, the source of its buoyancy also seems to be different. While normal mantle plumes rise as a result of heat exchange between the lower mantle and the much hotter core, this plume is not significantly hotter than the surrounding mantle. Instead, its buoyancy seems to mainly be caused by water. Electrical conductivity studies have shown that the mantle transition between Northeast Asia holds huge amounts of water, 5 to 10 times more than you would normally find here. This water was likely trapped here by more than 100 million years of continuous subduction and dehydration of the ocean floor along the eastern seaboard of Asia. Deep earthquakes in the stagnant slab seem to indicate that these dehydration processes are still going on today. Here's where the chart from earlier comes in. As you can see, earthquakes occur pretty much everywhere in the downgoing slab, but they seem to pick up again in magnitude and quantity once we get to this point, the mantle transition zone below Changbai Mountain. where we can see a visible cluster of deep earthquakes. These earthquakes may reflect the reactivation of faults deep in the slab caused by the horizontal bending of the plate. Near the Japan Trench, many normal faulting earthquakes occur in the outer rise portion because of the upward bending of the oceanic lithosphere before the plate's abduction. A large amount of seawater may enter into the deep portion of the Pacific plate through these normal faults. As the stress regime changes from extension to compression during the subduction, the normal faults are closed, and thus a large amount of water could be preserved deep within the slab. While dehydration processes of the overlying crust cause the commonly observed arc volcanism, the water stored deep within the slab is brought down to the mantle transition zone. Here, the stress regime once again changes because of the huge resistance at the bottom of this zone. As the slab bends and deforms, the preserved faults are reactivated, which allows for dehydration processes deep within the slab. How these dehydration processes look like in detail is, however, still subject to debate. The extreme temperatures and pressures, as well as the unique minerals found in this zone, make it difficult to predict how exactly the water interacts with the surrounding mantle.
Basically, Qinghai Mountain is formed by the same process that the other volcanoes further east are formed, by the dehydration processes, basically. When the water lowers the melting point of rocks, as it releases from the rocks and gets turned into magma, basically. A more viscous kind, too.
One thing, however, has become clear over the last couple of years, how exactly the water interacts with the surrounding mantle. One thing, however, has become clear over the last couple of years. The mantle transition zone below Northeast Asia, and likely elsewhere in the world, is an enormous water reservoir and likely plays a critical role in global water recycling processes. Thanks to the minerals in this zone that are particularly good at incorporating water into their structure, the mantle transition zone may hold more water than all the oceans combined. Below Qinghai Mountain in particular, it seems the water content has reached a critical amount, enough that the hydrous mantle becomes buoyant and starts to rise into the upper mantle. Here, it accumulates on top of the mantle transition zone and forms a hydrous plume. Convection processes in the big mantle wedge caused by the fast subduction of the Pacific slab likely further aid the plume's rise, and the reduction in pressure ultimately causes dehydration melting of the wet mantle rocks. The result is a continuous wet and hot upwelling right below Northeast Asia. So to summarize, Mount Pek-2 is not a traditional hotspot, but a sort of back-arc volcano caused by a hydrous plume that rises from the mantle transition zone and that is fueled by the subduction and stagnation of the Pacific slab under Northeast Asia. Detailed tomographic images of the other volcanic fields in the region show similar structures below them, indicating that they were the result of similar subduction-related processes. In fact, it seems the entirety of East China and the Korean Peninsula were heavily shaped by these mechanisms. If you map the western edge of the Pacific slab, you can find it lines up perfectly with the so-called north-south gravity lineament, an important geophysical boundary in East China, where the surface topography visibly changes. You can see it quite clearly on this height map. When you cross this boundary from west to east, the thickness of the continental plate dramatically decreases from around 100 kilometers or 60 miles to about 50 kilometers or 30 miles. The result is a significant reduction in surface elevation in Northeast Asia. That this boundary lines up so well with the Pacific plate below is no coincidence. Evidence suggests that the entire region was the result of millions of years of lithospheric destruction from below, caused by the continuous subduction and the subduction-related melting and upwelling of mantle material. The result of these processes was extensive large-scale volcanism and the formation of interplate volcanoes in Northeast Asia, of which Qinghai Mountain is currently the largest and most active of. While this might seem like a story about this one very unique volcano in a remote corner of Asia, it's actually much more than that. What the geodynamics of Northeast Asia have shown us over the last 20 years is that the mantle transition zone plays a key role in continental magmatism, and that the importance of water in these processes has been significantly underestimated in the past. And this has historically not just happened here in Asia. wet upwellings related to the subduction and stagnation of oceanic crust in the mantle transition zone may in fact provide a possible explanation for much of the terrestrial intraplate volcanism that has happened around the globe. Geochemical analyses even suggest similar processes are likely linked to the formation of continental flood basalts, which represent the largest volcanic events in Earth's history. These cataclysmic eruptions that covered areas of hundreds of thousands to more than 1 million square kilometers in lava are important points in our geological history, points that mark the rifting and breakup of continents or catastrophic mass extinctions. Conventionally, the formation of these provinces was, like their oceanic counterparts, attributed to the initial arrival of mantle plumes from the core mantle boundary, but the chemical composition of continental flood basalts is often distinct. Hydrous melt that seems to have originated from recycled oceanic crust could, for instance, be identified in the Siberian Traps and the Central Atlantic Magmatic Province, which instead implies a subduction-related origin. This means Changbai Mountain is not an isolated case. Instead, it has become an important window into processes that likely have in the past, albeit on a much larger scale, not just played a key role in the formation and breakup of continents, but also severely impacted the course of evolution on a global scale.
Yeah, the Siberian traps were really bad. Good video, right? Anyway, let's...
The past, albeit on a much larger scale, not just played a key role in the formation and breakup of continents, but also severely impacted the course of evolution on a global scale.
Yeah. Great. I muted my mic. Good video, right? You guys can still hear me. Okay, that's not good. Alright, that's not good. I guess the only way to truly mute myself is to actually plug out the this thing right here. Basically, that's the best way to basically, yeah, actually mute myself. Let me try to... I bet you guys can still hear me probably. That's the best way to basically, yeah, actually mute myself. Let me try to... I bet you guys can still hear me probably. Okay, this is bad. Okay. Okay, this is bad. Okay. Let me see what I'm doing now. So Airbus A320. Okay, when I'm going to mute myself, the only way I can mute myself is to unplug this. So Airbus A320. Okay, when I'm going to mute myself, the only way I can mute myself is to unplug this. Okay, guys, I'm back now. Okay, guys, I'm back now. Let me edit this. I don't know what is wrong. Hold on. Okay, I'm trying to basically. Okay. Yeah, basically, I don't know how to. Disabled. Set its audio device to disabled. Hold on. I'm just having some technical difficulties right now. Just need a couple.